So the n by n identity matrix is a square matrix with ones along the main diagonal and zeros elsewhere. So, for example, the 2 by 2 identity matrix would have ones on the main diagonal and then zeros everywhere else. The 4 by 4 identity matrix would have 4 rows and 4 columns, and then we would have ones along the main diagonal and zeros everywhere else. So that would be an example of the 4 by 4 identity matrix. The identity matrix behaves like the number 1. If I multiply the number 1 by anything, what happens? Well, it stays the same. So for every matrix A, I have A times I equals I times A equals the original matrix A. Just like with numbers, if I multiply by 1, I don't change anything. Well, if I multiply by the identity matrix, I also don't change anything. So, like for example, 3 times 1 is equal to 1 times 3, which is equal to 3. Or for any number x, x times 1 equals 1 times x is equal to x. Because 1 times anything is just the anything in question. All right. So now we have a theorem that we know very well. It says every non-zero real number A has a multiplicative inverse. The multiplicative inverse of A is A to the negative 1 power, which is 1 over A. So for example, what is the multiplicative inverse of the number 3? Well, 3 inverse would be 3 to the negative 1, but if you have a negative exponent, you move it from the numerator to the denominator and you get 1/3. So we'll notice, well then, what is 3 times 1/3? Well, that would be 3/3, and 3/3 reduces to 1, and that's our multiplicative identity. Interesting. So now, using exponents, we would have the following. Well, what's 3 times 3 inverse? Well, if you multiply two things together that have the same base, you add their exponents. So that's 3 to the 1 plus negative 1, and 1 plus negative 1 is 0. And what's anything raised to the 0 power? 1. Which is also the multiplicative identity. Interesting. So let's take a look at example number 3. So we want to solve this equation using the multiplicative inverse. Well, we just talked about finding the multiplicative inverse of 3 was 1/3. So we have the equation 3x equals 12. Normally, if we were going to solve this equation, we would say, oh, well, we have 3 times x, so we would divide both sides by 3. Well, instead of dividing both sides by 3, what if we multiply both sides by the multiplicative inverse of 3? So we multiply by 1/3, and we multiply by 1/3. Well, 1/3 times 3 equals 1. They cancel out, and I get just x. And what's 1/3 times 12? Well, 1/3 times 12 gives me 4. And we'll notice that that's the same thing that you would get if you divided both sides by 3. So you're probably at this point thinking, well, you're just playing semantic games with this now. Well, maybe, But I don't think so. Because what we're really discovering is, once again, mathematicians told you a lie for a very, very, very long time. There's actually only two operations, addition and multiplication. We can add opposites, which is how we subtract, or we can multiply by inverses, which is how we divide. And that's the reason why we have to have the order of operations, and why things don't commute, is because we're using these artificially made operations, and they just cause problems. So we're going to see that we can get by without using any of these things. All right, so to resolve this, we're going to multiply both sides of our equation by 5 inverse. And in this case, that's going to be 1/5. 1/5. The 1/5 and the 5 reduce out, and we get x is equal to 1/5 times 125 is 25. And that would be the solution to our equation. All right, so let's take a look at example number 4, I believe. So find the inverse of the matrix A. All right, so to find the inverse of A, we join A with the identity matrix of the same size. So we create a new matrix, and we're going to have the matrix A, and we are going to join it with the identity matrix of the same size. So in our case, we have a 2 by 2 matrix, so we're going to have 3, 1, negative 17, negative 6, and we're going to join it with the matrix 1, 0, 0, 1, so the identity matrix of the same size. And we'll notice that this new matrix has order or size 2 rows and 4 columns. We need to reduce this matrix into Rref, so we're going to convert the matrix to Rref. So we're going to put that matrix into our calculator. And it is a 2 by 4 matrix, so we go 2 by 4, and we have 3, negative 17, 1 and 0, and 1, negative 6, 0 and 1. And then we go second quit, second matrix, we go over to math, and we scroll all the way down to Rref, not Ref, but Rref, second matrix A, and we get the following output from our matrix. Now, if the matrix has 1s on the main diagonal, the matrix on the right side is the inverse. So we'll notice that on this side right now, I have ones along the main diagonal. In essence, this is the identity matrix again. If that happens, then this is the inverse. So then A inverse is equal to the matrix that's on the right-hand side. So 6, negative 17, 1, and negative 3. If the matrix does not have ones on the main diagonal, then the matrix is not invertible. So that tells us whether or not we have whether the matrix is invertible or not, is if we end up with ones along the main diagonal. All right. So this is really the process that you would use if you were going to find the inverse of a matrix by hand. Turns out, if we ask our calculator nicely, it will find the inverse for us. So we'll notice example 5 is using the same matrix that we had in example 4, right? So before we do that, let's take a look at our calculator. So we've been using the x inverse key actually to find our matrices by going second matrix. But let's check something. If I go 3 inverse and I hit it on my calculator, I get 0.333333. And then if I ask for a fraction, what does it tell me the multiplicative inverse of 3 is? 1/3, which is what we would expect. We can use that same button to find the inverse of a matrix. So let's put our matrix in, which will be really easy. We go second matrix, we go over to edit, and just change it to a 2x2 matrix. And if you've been following along, it will be exactly the matrix A, because we had it entered, we just adjoined it to the identity matrix of the same side. So 3, negative 17, 1, and negative 6. We're done, so we can go second quit. Then we go back in, we go second matrix, we grab matrix A, and let's just ask for its inverse. So we hit the inverse key this time, and we press enter, and notice, what did my calculator give me as the inverse of matrix A? Oh, the same thing that we found above, right? So we manually did the computation, and we got 6, negative 17, 1, and negative 3. I'm going to say manually in quotes, because we had the calculator do the Rref instead of us doing it by hand, like what you would have done using the rules from, say, 9.2. All right. So let's... Yes, ma'am. All right. So let's take a look at example number 6. So it's asking us to do the same thing. And it wants us to find the inverse using the x inverse key. Okay, sounds easy enough. So I grab my calculator, I go into my matrix menu, I go over to edit, and I'm going to edit matrix B this time, because I want to keep matrix A in there. That's why I'm not using A again. And then I'm going to go 2, negative 13, negative 10, and 65. And that gives me my matrix. I go second quit, second matrix. I'm going to select matrix B this time, and I press my X inverse key. And when I do, this time my calculator tells me something different. It gives me this error where it says singular mat, which stands for matrix, and it gives me an error. Well, I'm going to do this the long way to illustrate what happens. So if I go back into my matrix menu, I'm going to go back to edit. I'm going to go down to matrix B, and I'm going to make it a 2 by 4 matrix. So I've got those, and I'm going to put the identity matrix on the right side. Okay, so I edit my matrix. I go second quit. I'm going to go second matrix, get my Rref to do my inverse manually. I go down to matrix B, and when I do so, I get the following output from my calculator. So when I did it the long way, like example 4, I notice I get a 1 on the main diagonal, but what's missing here? And what was our conclusion when we had something that wasn't a 1 on the main diagonal? So if the matrix does not have a 1 on the main diagonal, then the matrix is not invertible. So the long story short is when we see singular matrix, all this means is the matrix does not have an inverse. So you don't have to do any of that other stuff. So basically that error that says singular matrix just tells us that the matrix doesn't have an inverse. And the reason for that is if you did it the manual way, where you actually find the matrix, you end up with a matrix that doesn't have a solution because it has an inconsistent system. So it's not possible to find an inverse. So this is a little different from real numbers. In the real numbers, there's only one number that doesn't have a multiplicative inverse, and that's 0. With matrices, there are lots of matrices that don't have inverses, and that's okay. So don't let that bother you. At the end of the day, then, if you see singular matrix, what does that mean? That there is no inverse, and you're done. That's it. Okay. So now, for example number 7, we want to solve this by using the matrix inverse. So to do so, the first thing we're going to do is we write the system as a matrix equation. And remember, we did this, it was the last example in 9.4. So we get our coefficient matrix is going to be 3, 1, negative 17, and negative 6. Our variable matrix is going to be x, y, and then our constant matrix is going to be 2, negative 3. So this is our A times X is equal to B. So then step 2 is we put A and B into the calculator. So we grab our calculator, go second matrix, matrix A, oops, need to go matrix, then I go over to edit. Matrix A is 3, -17, 1, and -6. You'll notice we're recycling. If you type the previous example in, matrix A is already in your calculator. And then we go second matrix, we go over to edit, and we need to edit matrix B. And matrix B is a 2 by 1 matrix, so 2 by 1. And then we have 2 and -3 in our calculator. So now that we have those into our calculator, we put matrix A, matrix B into our calculator, and then 3, we solve A times X is equal to B by multiplying So we solve AX equals B, and we're going to multiply by A inverse on both sides. So if we have the equation A times X is equal to B, and we multiply on the left by A inverse, we know that A and A inverse are going to cancel out, so the left side is going to be X. So then the answer is going to be A inverse times B. So now we can calculate this on our calculator. So we open up our calculator, we go second matrix, we grab matrix A, but we don't want A, what do we want? A inverse, so we press our inverse key, times matrix B, so second matrix, and we select matrix B, and we press enter, and after our calculator thinks for a moment, it gives us the following as our product. So we found this on our calculator. So then what we have is the following. Well, what was matrix X? Matrix X was this matrix from the very, very beginning. So if we look, well, what was X? Well, that's X. So this is really XY is equal to 6311. Well, if that's the case, what does X have to be? Well, what's in row 1, column 1? 63. So X is 63. And what would Y have to be? So then the solution, the ordered pair X comma Y, is 6311. Interesting. So it's worth noting that you get the same answer if you write an augmented matrix and do Rref, right? It's just two different ways to solve the same thing. This is creating a new algebra involving matrices. So to resolve this, we write out our matrix. So first column is 2, 1, 5, 3, -4, and 1, 4, 3, and 1. And we have our variable matrix this time, which is x, y, z, is equal to 2, 2, -4. So the two matrices I'm really concerned about are A and B. So I go ahead and put those into my calculator. So second matrix, I go over to edit. And this time my matrix A is 3 by 3. So I have 2, 3, 4. And then 1, -4, and 3. And 5, 1, and 1. And then I go back, second matrix. I'm going to put in my matrix B this time. And matrix B this time is a 3 by 1 instead of a 2 by 1. So change its size, 2, 2, and -4. So I've got both of them in my calculator. So I just type A inverse times B again. And this time I end up with the matrix -1, 0, and 1. So just one word of caution. The most common mistake people make when doing this method is they forget the inverse and do matrix A times matrix B, and they forget the little -1. That makes a big difference. So then we get x equals -1, y equals 0, and z equals 1, or the ordered triple -1, 0, and 1.